4 dimensions. Okay, what did I say? So spin C structures are a little bit more complicated, and but for 4 manifolds they do exist. And from this data, remember that, you know, if we want to describe shortly what a spin C structure is, these are just 2 bundles, W plus and W minus, 2 U2 bundles together with a map from the complexified tangent bundle to the homomorphisms between these 2 bundles. So if you would like to think, you know, less abstractly, this is the data we have to fix. And out of this, I wrote down 2 equations, and I will just write down the equations now, but their shape is not particularly important for the rest of today, where A is a connection on the determinant line bundle of W plus, which is the isomorphic to the determinant line bundle of W minus, and I denoted it by L, and psi is a section of W plus. So these are 2 infinite dimensional spaces. The smooth sections of a bundle is typically an infinite dimensional space. The space of connections is also infinite dimensional, and we take 2 objects from those, and we consider the solution space of this differential equation. Why do I say differential equation? Well, the Dirac operator, if you remember, it was a composition of the Levi-Civita connection together with this Clifford multiplication. A connection is like a directional derivative. So you can imagine that this is some kind of a partial differential equation. Likewise, if you have a connection, then the curvature is given by differentiating that connection in some sense. I will not go into the details, but our motivation was to capture an invariant of the smooth structure by writing down a differential equation which is given by some convenient data. And here the data are the spin C structure and the metric. And our goal was to say that what we will do is to count how many solutions do we have. Miriam, you will read me the chats every now and then. That's very convenient.
I will. Right now there's just technical things going on.
Technical, you can spare me those, but when it comes to something interesting, please.
Will do.
Okay, so so the slogan is count solutions. And it's much easier to say that slogan than to actually carry it out. Here is the first obstacle of counting solutions. So the first problem is that if we have one solution, we have a lot more. So here is a group G, which is just the C infinity maps from our 4 manifold to S1. So again, this is an infinite dimensional group. And the group multiplication is just multiplying the image. And then if we pick an element from that group, then we can act with that element on a solution A psi. So let's send psi to minus G times psi. So we have a section, then we can pointwise multiply it with a unit complex number, and then we get another section of the same bundle W plus. And for the connection, we can send it to the connection plus a 1 form, which in this case is 2 times dg. So that will be a 1 form on the manifold X. And if you have a connection and add the 1 form to it, we will get another connection. And then the fact is, if A psi solves the equations, then so does this new pair, A plus 2 dg minus G times psi. So that's not such a great news. It just says that just by purely counting solutions, will not work, because if we have one, we have at least that many. And this is an infinite dimensional Lie group, so we have too many. Of course, the idea is then, why don't we just quotient out by the action of this group on the space of solutions? So let's take the space M, which is just the solutions of the equations divided by the action of this big group G. And that's a fantastic idea. Then we hope that we will get something which can be counted. Of course, what can we count? So that's the question. And so we want the following. We want this M should be a zero-dimensional manifold. So a couple of points. We would like to see that this is compact. Another property, we would like to see that this is oriented, which for a zero-dimensional manifold is just an association of a plus or a minus sign to every point. And then we can make sense of the count of the points in M. And we would like to see that this number is independent of the metric G. And if we can carry out all these, we can make sure that M satisfies all these properties. Then we can define a function, Seiberg-Witten, which goes from the space of spin C structures of X to Z, and for a spin C structure, it associates the number in this space curly M, right? So, so that would be an optimal scenario, and then let's see whether this holds or not. And in some cases, it will pass through, and then there are some problematic cases. So let me just very quickly sort of recap what goes through without problem and when do we have something where we have to do something. Okay. So is it a manifold? Well, so let me just sort of recast and do the following. Define the Seiberg-Witten function which associates to A psi the first equation on the first coordinate and then the difference of the two sides of the second equation like this. And then the solution space is obviously the inverse of 0. So, and or M is just the solutions over the group G. So when can we make sure that this resulting object is a manifold? Well, we would like to see that this guy is a manifold, maybe of infinite dimension, and this group acts freely on that manifold. And then we hope in finite dimensions that would be sufficient. We need a little more in this case, but as we will see, none of these assumptions come for free. When can we say that the solution space is a manifold? Well, this just says in finite dimensions, it would mean that 0 is a regular value of this Seiberg-Witten function, which might not be the case. We know that regular values of a function are dense, but we don't know whether 0 is one of them. So we would like to make a little bit of a change in the setting, and let's define script S to be the union of these solutions for all G. Remember, we had to pick a Riemannian metric G, and now we take the union for all G. We have to equip it with some metric, and we do have a map to the space of metrics. every solution is a solution for some particular metric, and we associate it to that. And the fact is that S is a manifold. So now we apply a version of Sard's lemma, which says that in the target we have plenty of regular values, and then we just pick one and we consider that to be our chosen metric, and then we have a good manifold type solution space, still too big because there is this group action which we have to take into account. Okay, so that sort of takes away one problem by choosing the appropriate metric. What happens with the group action? So I leave the action on the board. And so the question is, so what are the fixed points? So when do we have a fixed point? Well, this is not very hard to understand, because when do we have a fixed point? When does it happen that A is the same as the result of the action by one of these group elements? This just means that this term should be 0, i.e. G is some constant function. So it maps from X to S1, and it has to take one value for every point of X. But then psi being equal to minus G psi says that so this will happen if psi is identically 0. So those are the fixed point where psi is 0 and A is something else. In this case, this equation is satisfied automatically because psi is 0. And then we have the other equation, which becomes a sort of a topological condition. Remember, Fa is representing some number times the first Chern class of the bundle. It lives on. So this is a topological quantity, and we have to vary a little bit what does this plus mean. But the fact, what I would like to get to is that if the manifold has B2 plus bigger than 0, then G will act freely on the solution space. So we are getting closer. We have to pick a generic metric, and we have to assume that our manifold satisfies some topological condition, and then M is a manifold. Well, the dimension of this manifold can be computed by a simple formula, which I will not argue why is this the case. So we take the first Chern class of this determinant bundle. We take the square. This is a degree. It is a 4-dimensional cohomology class. We integrate it over the fundamental class of the manifold. We get a number, and then we have to subtract some topological terms, and the end result is the dimension. So in order to have a 0-dimensional space, we have to assume that this is equal to 0. And if X admits a complex or even almost complex structure, then there is a spin C structure such that this dimension is equal to 0. So again, the upshot is that we start with a manifold. If we pick the metric carefully and we pick a spin C structure carefully again, such that this quantity is equal to 0, then we will get a 0-dimensional smooth manifold as my M. The second line was whether it is compact or not. The good news is we don't have to do anything. It will be always compact. M is compact. And I will not go into the argument at all. This relies on a formula in differential geometry, which is called the Weitzenberg formula from Weitzenberg. And I'm not planning to argue for that. I will skip the orientability. We can orient this space. So we will get an oriented 0-dimensional manifold. That's fantastic. This is characterized by how many points we have in that, counted with sign. And so we have, at the end of the day, a number. And let me just say a word about the last issue. So how does it depend on the metric? So we have M corresponding to some metric G0 and some other M corresponding to G1. And for a fixed spin C structure, well, we can consider MGT, where GT is a one parameter family of metrics connecting G0 to G1. And once again, for a generic choice of this path, this will be a manifold. We again have to worry about the potential problem of having fixed points of the group action. This can be avoided if we also assume that this B2 plus is bigger than 1. So it's not only for one particular metric we can avoid the problematic solutions, but a whole one parameter family. And once this is satisfied, we know that when count these spaces with sign, we get the same number. So this was a very quick, hopefully not super confusing summary of how Seiberg-Witten invariants are defined. I left out even I tried to touch upon a lot of details, but I skipped a lot. For example, I quoted the Sard-Smale theorem, saying that every element, most of the elements in the image are regular values. But in these theorems, when you prove it in that setting, in the infinite dimensional setting, you need some kind of completeness. So instead of C infinity objects, we have to complete our spaces, and then everything becomes much more complicated and much more analytic. I will not go into that. I will summarize the invariants in a few properties. But before doing that, let me just sort of give you some advices. So there are various levels you would like to understand these notions. And here I gave a roadmap. So the first level is just to get the feeling how these invariants are defined. I wanted to say that you want to get the vibe, but maybe that's too informal. So a rough picture. That's level 1. I hope everybody got some feeling, how these things are defined. The next level is to understand spin C structures. This involves a little bit of working with bundles. The next level is to understand the bundle constructions I did, like how to define these operators and what are connections, and see what are the relations between these objects. The next level would be to understand the formal properties of Seiberg-Witten invariants, which I will do today. And then we are getting close to really high level understanding, like go through the analytic details of the definitions, and at the end, get the full package. But this is only if you would like to do research very particularly in Seiberg-Witten theory. For our purposes, this intermediate level of understanding the formal properties will be sufficient. But I wanted to tell you how these constructions roughly go to have a better feeling. We'll see how successful it was. in any case, here are the two theorems. So let me just summarize again. So what did we get at the end? So once again, X, smooth, closed, oriented, four manifold. Then the Seiberg-Witten function is a function from the set of spin C structures to Z. And let me remind you that every four manifold has spin C structures, and they are in one-to-one correspondence with the second cohomology of the four manifold. And let me just remind you that for a closed oriented four manifold, the second cohomology is actually the same as the second homology. So it's a little bit unorthodox space, but it's not so weird. We know exactly the rank. If X is simply connected, then it's just a Z module, a free Z module of rank B2, the second Betti number. And so the main property is this, that theorem that SWX is a diffeomorphism invariant, once B2 plus of X is bigger than 1. We did need that assumption in order to pass through, to get rid of the fixed points of the group action, i.e., if F is a diffeomorphism between two four manifolds, then, so how do we write that down? Seiberg-Witten of X2 at the spin C structure S is the same as the Seiberg-Witten of X1 on the pulled back spin C structure. Once again, spin C structures are like second cohomologies, so you can pull them back. And I write down that equation. It's not completely true because there might be a plus or minus, but what we will be worried about in the future is when these terms are non-zero, right? So zero or non-zero will be really the deciding issue. So we say that S is a basic class of X if this value is non-zero. And likewise, in this case, C1 of S, which is in the second cohomology, is also called basic class. So the set of basic classes is denoted by this Bx. And as the Seiberg-Witten function is a differentiable invariant, this set is also a differentiable invariant. Here's a fact. Bx is always finite. So at this stage, you can forget about how this differential equation was defined. We either have a set of second cohomology classes or just the cardinality of this set. So in particular, Bx, the size of this set is a diffeomorphism invariant. Sometimes to actually understand the entire set is kind of complicated. You have to work in the set of spin C structures or inside the second cohomology. But for example, to understand its size, that should be, that's at least it's very easy to compare. And so I will start this formal understanding of the properties of Seiberg-Witten theory by two theorems, a vanishing and a non-vanishing theorem. So here is the vanishing theorem. So theorem vanishing. And it sounds as follows. So suppose board. The beauty of online teaching, right? So suppose that my four manifold X is a connected sum of two other four manifolds, X1 and X2. That can happen with four manifolds. You know, we have this operation of taking a connected sum such that the B2 plus invariant of X1 and of X2 are both positive. Then the Seiberg-Witten invariant of X is constant 0. So putting back in the language I just introduced, the set of basic classes of X is the empty set. Right? There is no spin C structure. You would expect that for particular metrics, for every spin C structure, the corresponding solution space might be empty, and you don't count anything. And indeed, this is how you prove it. You know, the connected sum of two manifolds is just somehow to join them by a tube along S3. And what people do in trying to prove this theorem is to introduce metrics with longer and longer necks. So it will look more and more like a very long bone. And then in the limit, you find that if you have a solution for the connected sum, then you would have solutions for X over X1 and over X2. But when you glue them together, there is a choice involved, and you would get more than zero-dimensional space, which is a contradiction. So I will not work out the details, but this is what you have to remember. If a four manifold decomposes as a connected sum, and the two sides have satisfied some very mild algebraic topological property, then the Seiberg-Witten invariant vanishes. Corollary: if you take n times CP2 and any copies of CP2 bar. So this is a fantastic four manifold made out of projective planes and projective planes with the opposite orientation. And n is bigger than 2, then we can decompose our four manifold in this way, because you just put a CP2, at least one on both sides. If we have 2, then we can do that. And this X has vanishing Seiberg-Witten. Everybody is smooth. All the manifolds are smooth. X1 is smooth, X2 is smooth, X is smooth, the connected sum is smooth. For topological things, this whole theory just breaks down. You know, you don't know how to do Levi-Civita, so everything is smooth. Okay, so I don't know, is it a good result or a bad result? I mean, you are not really happy when you define with lots of effort an invariant, and then somebody comes and says that in many cases it's 0. It might happen that it's 0 all the time, and then you didn't do anything. Well, luckily this is not the case. So here is the non-vanishing theorem.
Andras, we have a question in the chat. Is it known what happens when n is less than 2?
When n is equal to 1. So there are two other cases, right? 0 and 1. If n is 0, then this is a negative definite manifold. And if you remember, then we will have a problem of defining the whole thing, because this M, in the definition of M, the group does not act freely, so we don't really know how to count it. If n is equal to 1, then the individual solution spaces might be assumed to be manifolds, and the group can act freely. But when you go from one to the other through a one-parameter family of metrics, then you will hit points where the group does not act freely, and you don't know how to relate these invariants. I mean, we don't know it now, but people do know how how to go from one metric to the other, but you don't get such a simple-minded invariant. I mean, it's a much more complicated story, and you don't get that outcome. Does that answer the question? So we already went through this. So notice that, yeah, maybe I should point out that n is exactly B2 plus of x, and m is B2 minus of m of this 4-manifold x. So, you know, we always assume that this should be strictly bigger than 1, which is the same inequality as n is at least 2. Somehow 4-manifold topology, you know, doesn't satisfy the Constitution of the United States. Not all 4-manifolds are created equal. The B2 plus equals 1 4-manifolds are slightly different, and we have to develop special tools for them. That's how it is. Okay, so what's the non-vanishing theorem? This theorem is due to Cliff Taubes from 1994, and it says the following. So suppose that X is a symplectic manifold. This concept appeared yesterday in the research talk, but let me just very quickly remind you what it is, i.e., there is a 2-form on X such that this 2-form is closed and non-degenerate. So if you wedge it with itself, then you get a top-dimensional, 4-dimensional form, which is always positive. Then there is a spin C structure of X such that the Seiberg-Witten of X at S is plus or minus 1. And I, of course, forgot the running condition that B2 plus of X is bigger than 1. So whenever we talk about Seiberg-Witten invariants, we have to assume that topological condition. Otherwise, the whole story has a much more complicated definition. Okay, so does that make sense? It does. It's not so important that we have the value plus or minus 1. What's important is that it is not 0. Okay, let me just spend a minute or two on symplectic manifolds. So where does this concept come from? So suppose suppose that X is a complex manifold. So this just means that instead of having local charts corresponding to Rn, we do have maps which take you to Cn, and when you go from one chart to the other, then the maps are not only differentiable, but they are complex differentiable. They are holomorphic maps. So in particular, you can multiply with I in these charts, and so we can consider the following. Consider a metric G on X and define a 2-form omega by the following conditions. So we have 2 tangent vectors X and Y, and we would like to evaluate this 2-form, and we do the following. Instead of just applying my metric on X and Y, I apply it to X and I times Y. So I use the complex structure here and the metric there, and this will be a 2-form. This is just a 2-form on X, and G is a Kähler metric if this omega is equal to 0. So it's of course, it's a very long story, which I will not outline, but somehow this metric looks locally very much like Cn if this condition is satisfied. And notice that it's not very hard to show that this omega will always satisfy that the n-fold wedge product is positive. So the non-degeneracy assumption of a symplectic form is always satisfied, but this one, once again, a differential equation is not. And it's just a condition. And symplectic is sort of, you just distill from this long story the fact that you just look for the two form which satisfies this and the non-degeneracy. Well, 2 omega for a 4-dimensional manifold and more if your manifold is higher. Today we concentrate in 4 manifolds. Okay, so this notion was around, and then the theorem of Taub says that if X is a smooth manifold which carries a symplectic structure, then this Seiberg-Witten invariant is not constant 0. So what are the examples of such manifolds? So here is a fact. CPN is scalar. Obviously, it's a complex manifold because we just create it from Cn plus 1. We just take the space of lines in a one higher complex vector space. And it requires a little bit of a patience to write down the actual metric. And from the metric, the actual omega, which just shows that this is a scalar manifold. And the next fact, which I leave you as an exercise, it's really easy, that if X is scalar and Y is a complex submanifold, then Y is also scalar. Just have to check that if you have an overall 2 form on X, which is closed, then the restriction will be also closed. It's a very simple exercise. And now this allows us to find the first exotic smooth closed 4 manifold pairs. Namely, we have to remind ourselves on the second lecture, sorry, I have to change the board. On the second lecture, I introduced an infinite family of complex surfaces. You remember the SDs? These were just those Z0, Z1, Z2, Z3 points with homogeneous coordinates in CP3, which satisfy this equation. And it was an assignment to try to understand what is the Euler characteristic, the signature, and the type of these manifolds. And I gave you the result, and it's not I'm not saying it's an amusing assignment, but it's a work with Chern classes, and it's not very complicated. Nevertheless, fact SD, and now I have to come up with the precise numbers. 27 CP2 connected sum, 44 CP2 bar have the same. So first of all, fundamental group, they are both simply connected. Euler characteristic, signature, and type, both odd. So once again, to compute these numbers for this manifold is a triviality. To compute it for, S5. To compute it for S5, that relies on the solution of that homework assignment. But now by Friedman, S5 is homeomorphic to, I don't know, let's call it Z. Homeo to to Z. That's, you know, we rely on a very abstract theorem, which hopefully becomes less abstract after you go through Aru's lecture series, but we don't see any particular homeomorphism between the two. We just know that this theorem just provides one. But the Seiberg-Witten invariant of Z is identically 0 by the vanishing theorem, because the n in the theorem of the vanishing theorem is now 27, definitely bigger than 2. So we don't have any interesting Seiberg-Witten story here. On the other hand, S5, by its very definition, is in CP3, which, as every CPN, is a scalar manifold. So S5 is scalar. So in particular, it's a symplectic manifold. And by Taub's theorem, the SW of S5 is not identically 0, although this is a diffeomorphism invariant. So S5 and Z are not diffeomorphic. So this is the first encounter of exotic four-manifold pairs, closed smooth four-manifolds. You might ask, why did I pick S5? And so if you do even numbers, then the type is even. So you cannot compare it to such simple-minded guys. You have to put them up from other surfaces. It's a little more complicated. And if you take S1 or S3, then indeed they will be homeomorphic to some connected sum of some CP2s and some CP2 bars. But there, the number of CP2s will be 1. So our vanishing theorem does not apply so nicely. And indeed, they will be diffeomorphic. So S1 is just CP2 itself. And S3 is CP2 blown up in 6 points or something like that. I don't remember the actual numbers. But this is the first when you have something truly unique happening. Such an example does not happen in dimensions 0, 1, 2, 3. Whenever a two lower dimensional manifolds are homeomorphic, then they are indeed diffeomorphic. So in dimensions less than 4, there is no such exotic phenomenon. And so we see the first one. In any other dimension, in any higher dimensions, there might be exotica like this, but there is always a finite amount of exotica. So somehow there are only finitely many smooth 15-dimensional manifolds, which are all homeomorphic to each other, but pairwise not diffeomorphic. There is no way you can find infinitely many. Well, the situation is very different in this dimension, as I will try to demonstrate maybe next time. Let me just say a word about how to prove this theorem. So how does Taub's prove this theorem? Well, you have to remember what we are looking for is to show that for appropriate choices of metrics and for the species structure, there is a unique solution up to sign. So if you just add them up, or more preferably, there is one single solution, period. And so to this matter, Taub's considered a little perturbation of this equation. And so where did I write that down? Yeah, so the symplectic form itself and this is just a real number. So when R is equal to 0, then we just get back the original equations. And then we start to go with R to infinity. And then what happens is that if it is large enough, then he managed to show that this system of equations has a unique solution. So it is very much tied to the actual form of the equation. And it turns out that we can sort of translate this very differential geometrical equation into some holomorphic looking object, and then some standard analytic arguments just tell you that you have, for very large R, there is a unique solution. So this is a little different change of the equations, and you have to argue that this is also okay. If we take the solution space for this perturbed equation, it's as good as for the original one. Once again, a whole bunch of analysis is involved in that step. Okay, so I did not give you proofs. I only gave you sort of ideas how to prove these facts. And the only exotic pair we have so far is S5 and my fantastic 4-manifold Z here. So this is an exotic pair. Of course, if you are sufficiently patient, you can come up with an infinite amount of examples of the same type. You can just take the odd Ds instead of 5 and determine the corresponding connected sum of CP2s and CP2 bars, and you will always get exotic pairs by the same reasoning, vanishing and non-vanishing theorem. Okay, so I gave you two important tools in cyber-Witten theory. Let me give you a third one, which comes up in Lisa's lectures. And that's the adjunction inequality. So we will not really use that, but let me just state it. And it says the following. So suppose, so once again, as always, X is a smooth, closed, oriented 4-manifold. And now, as we are in this cyber-Witten world, we also have a running assumption of the B2 plus of X being bigger than 1. Okay? So we do have the cyber-Witten function, and suppose that sigma is a two-dimensional surface smoothly embedded and also this is also a closed surface. A closed embedded surface, of course, can be triangulated and you have a homology class. So there is a corresponding homology class and it has a property such that the self-intersection, which remember is just the value of the intersection form when you feed it with twice this homology class, or if you like to view the intersection form on cohomology, then you have to replace these guys with their Poincare duals. And we have to assume that this is non-negative. And there is one more assumption that the genus is not equal to 0. Then, okay, suppose furthermore that the cyber-Witten function on some spin C structure is not equal to 0. So you do have solutions for that particular spin C structure. Then, and now comes the inequality, it just says that if we take the first Chern class of this spin C structure, so remember, there was this W plus and W minus two U2 bundles, and they had isomorphic determinant bundles. That's the line bundle for which we take the first Chern class. So this is a very simple second cohomology class. And we evaluate it on this homology. And we add this self-intersection, sigma squared. I dropped this 2 over sigma because there are just too many 2's. These 2 indicate that this is two-dimensional. This is two-dimensional. This 2 indicates it's a square. And then I drop the two-dimensional 2. I put it an absolute value. And this is always less than or equal to twice the genus minus 2. Okay, so this is the formula. So this just says that if you have an embedded surface, representing a certain homology class sigma. Then there is a lower bound for the genus of that surface, provided there is a non-zero Seiberg-Witten value. If all the Seiberg-Witten values are 0, then you have no idea, and there is no constraint. And from that perspective, you cannot work. The adjunction inequality tells nothing because it doesn't exist. But if you have one guy, so this assumption just says that no matter what metric you pick, there is always a solution of the equations, then you have this inequality. And as before, the way to prove that is you just take your sigma and you just try to pull it away, which means that you take a metric on x such that sigma is getting sort of further and further away, very similar to this bone picture I had before. And then you have to study the limit, what happens in the limit. And again, you invoke some fairly standard differential geometry to say that if this inequality is violated, then you get to a contradiction. So I'm not planning to talk about the adjunction inequality at all, but this sort of resonates with the slogan Lisa was propagating, that the difference in smooth structures somehow is reflected by the genus function. Every homology class admits a minimal genus representative, right? You don't have to check that the minimality exists because every guy can be represented by some surface, and then there are only finitely many lower options, and then you just try, or somebody tries, and then you get the minimum. And this Seiberg-Witten function gives a way to bound that under favorable circumstances. And you know, Seiberg-Witten theory is like magic. Sometimes it works, and sometimes it doesn't. For a 4-manifold, which is a connected sum of two pieces, both have B2 plus bigger than 0, then the Seiberg-Witten of X is constant 0, and you don't get anything out of this theorem. And that can happen. Okay, so the next goal is partially a goal for today, and this is where we will continue next time, is that we do have exotic pairs, but I claim that we have much more than that. So the next claim we would like to work on is that there are topological manifolds, 4 manifolds, with infinitely many differentiable structures, i.e., there are examples x1, x2, x3, and so on, such that all xi's are homeomorphic and no two are diffeomorphic. And the plan is to give a construction, and then for the end results, we will use Friedman's theorem to verify that they are all homeomorphic. And I will make a claim about the set of basic classes, and it will turn out that the number of basic classes, remember, these come all with this set Bxi, and I will take the cardinality of these guys, and let's call them, I don't know, Di, and it will happen that in my infinite family, no two will have the same number, so they are not diffeomorphic. So that's the plan. I should make one remark that we will construct a countable set, a countable infinite set of such, and it follows from some mild set theoretic arguments that on a compact X, there cannot be more than countably many different smooth structures. So, you know, as far as cardinality goes, this example shows the most. If X is not compact, this is not true anymore. And probably you heard about this famous statement that on the standard R4, there are uncountably many different smooth structures. So for non-compact manifolds, things are even worse. But for compact manifolds, things are not that great either. We know lots of examples where we have infinitely many smooth structures, but we don't have a single example where we would know that there are only finitely many, except if there is none. So far, the number of smooth structures on a 4 manifold is 0 if it doesn't have a smoothing, or we have no idea, or we have infinitely many. And even when we have infinitely many, we never have so far a complete list. And I will try to make an attempt to convince you that it's not expectable in the near future to have a complete characterization, because these examples are like a zoo, you know, all kinds of constructions, and they interfere with each other, and we have no idea how many different structures we can have. There are infinite lists, and we don't know how they intersect, and we have no idea whether their union is complete or not. Most probably they are not. So I think my time is up. So this is what we will do next time. And the topological 4 manifold I would like to pick is the K3 surface. So if you have a little time, and I advise you to grab the opportunity and maybe talk to the TAs about that. There will be a TA session in the evening and tomorrow before the lectures. K3 surface is S4, and also in the elliptic definition E2, and it would be very nice to see the topology of the K3 surface. For example, I will use the fact that there is a fibration of E2 over CP1, where most fibers are smooth tori, but there are a few fibers which are nodal curves. And actually, I will use only one nodal curve, but you have to convince yourself that there is this 4 manifold, which is a Kähler surface, but has a fibration which contains a nodal curve, and our construction will start from there. So this is the end of today's lecture. I hope to be more geometric next time, and I will take my chances to sort of build up configurations in these 4 manifolds. And if you have questions, I'm happy to answer now, or I leave it for Stefan and Marco today and tomorrow. Okay?
Okay, let's thank Andreas for the talk. Are there any questions for Andreas?
I have a question about connect sums of CP2s and CP2 bars. What's sort of the best known exotica among those, the smallest N and M?
So, of course, I deliberately skipped the N equals 1. But if you, can you hear me?
Yeah.
Okay. So, you know, I sort of work today with the N bigger than or equal to 2 case, but if you work a little harder with these Seiberg-Witten kind of theorems, then you can make sense of invariance for N equals 1 as well. And among these guys, we do know exotica if M is equal to 2, and we have no idea when N, so we do have infinitely many, and this is open. So this is just CP2 connected some CP2 bar, or if you like, this is the twisted S2 bundle. You might actually try to see that, or again, consult with the TAs. This is a worthwhile assignment. It's good to see that it's an S2 bundle. This is completely open. And of course, the M equals 0. So what happens on CP2, that's again wide open. And notice that this can be thought as some kind of a compactification of C2. We don't know the answer. There is another compactification of C2 where we view it as R4, and that gives you S4. That's the Poincare conjecture. So it's like half the Poincare conjecture or the complexified version. We have no idea. The good news is that here we don't have any tools. For CP2, in theory, we do have the tools. We just don't have good examples, and we have no idea what's going on. That's very sad. Or it's very happy. I mean, it depends on the stage you are at in your career. If you are an early researcher, you should be happy about having lots of unsolved problems. Well, I am an old guy, so I would like to see the solution of that. So please, guys, you know. Any other questions?
How about when n is 3?
N is 3. So now you got me. So this is 3 CP2. And so I know that I wrote a paper probably maybe 1,000 years ago, something like that, where we produce infinitely many examples so on 14. And I'm sure it has been reduced. But for example, what happens with 3, I'm almost sure that this is wide open. And if it goes beyond 3, again, we don't know anything. And it would be fantastic to say something about 3 CP2. And we don't know. Again, we do have the tool. Cyber-Witten theory is fantastic and well-defined. We don't know any potentially good construction of a closed 4 manifold, which is homeomorphic to 3 CP2. And we would be able to compute the Cyber-Witten invariants, and then, you know, potentially it's complex surface or symplectic or something like that. We don't know. I will talk a little more about these kind of geography problems, but maybe I'm not completely sure what is the best here. If I have to bet, I would say something like 8 or 9. Maybe I'm too optimistic, but something like that. Those are good exercises to try to combine all the constructions I will talk next time, and to cut down these numbers. And if you can go below what's known now, you know, that's quite an achievement. It is a very steep hill. If it gets very close to 3, it's harder and harder to reduce the number. And 3 CP2, I have no idea.
So the point of a lot of these constructions is to sort of do some sort of blow down operations, or like these like star surgeries, as I guess Sumero was talking about. But the idea is you want to stay within the symplectic world so that you know non-vanishing from Tops's result or something like that.
Yeah, I would give up symplectic and then just prove non-vanishing directly with some other methods, you know. And you don't have to do what we heard yesterday. There are other operations I would like to introduce tomorrow. And so far, believe me, I tried a lot of configurations and it never wanted to work. But it doesn't mean that it's impossible, you know. Maybe for a physicist, it would say that it's not possible, but not in mathematics. I tried hard and it didn't work. What does that mean? So yeah, these are very interesting problems, and I would like to sketch a few of them tomorrow. And some of them are, I would declare, not very hopeful. Let's put it mildly. Like this one, this one. This is also hard. When you reduce this number, that's hopeful. You know, that's a good direction to try your methods and your topological instinct to find exotica on these closed form manifolds, but it's not easy.
What is special about 3?
Well, that was the question. The larger the B plus is, the more examples you know. So now I don't know the exact number, but maybe for 55, there is an exotic structure here. So, you know, this is also a slogan somehow. The less topology you have, the harder to create an exotic structure. I was planning to talk about that tomorrow, so I will return to that. But somehow when these numbers start to grow, then you have more directions, more constructions, and it's much easier. If they are getting small, then things are harder. But there is nothing special in 3.
Great. Seems the time is 11:19 already. So if we have more questions, welcome to ask Andreas during the lunch. Let's have 5 minutes break so that we can come back at 11:25 for Lisa's talk. And let's thank Andreas again for this great talk.
Thank you.